Okay, so first left is an f of negative 1 times the width of 1. Second left is f of 0 times 1. Next one is f of 1 times 1 plus f of 2 times 1 plus f of... Now, how do I know when to stop? When you have 5 of them. Okay, you have 5 of them. I now have 5 of them. Now, we didn't go all the way to 4, but that makes sense, right? Because your last left would be there. If the curve was coming up like this or whatever, your last left edge, I'm so excited about what we're doing today, I just can't even think straight. Your last left edge is at 3, f of 3, okay? All right, so there it is. Now, what if f was given to you as an equation? What would you now do to get f of negative 1? Plug in a negative 1 for x, right? What if it was a graph? You would just read the y value at the graph. What if it was a table? You just read the table, you'd go when x is negative 1, you'd read the output, right? That's it. That's it. So once you've put it in f notation, then you can pay attention to what your actual function is. Okay, and maybe it's a calculator problem, so you can go and do some stuff with the calculator, or maybe you have to add it up by hand, whatever. Okay? All right, now what if it would have been R5? So the first one would have been at F0 times 1 plus dot dot dot. And the last one would have been F of 4 times 1. So you don't start at the far left edge when you're doing a right rectangle. Your first right rectangle height would be there and then go back. Okay, what if it was a midpoint? F of... So again, if you just, and that's why I sometimes just draw myself a little x-axis with my markings so I know where my subintervals are. And then from there I can find everything I need. I don't even need the function. I don't care what the function is. I just need to know where my subinterval endings are. And again, it's 1, and then f of 0.5 times 1. And then what would be the last one? 3.5 times 1. Again, if I do that right, I should end up with 5 of them. Okay, and then finally, what if it was a trapezoid? First trapezoid would be 1/2 f of negative 1 times 1, 1/2. Because you have to use the 0 again, right? Because f of 0, if you're doing a trapezoid, f of 0 is the right edge of the first trapezoid and the left edge of the second trapezoid, right? So you end up using them twice. Matter of fact, you'll use them all twice, but the first and the last, right? So your very last one would be 1/2 f of 3 plus f of 4 times 1. And so you'll use the f of negative 1 once, the f of 4 once, and then you use the other ones all twice. Now that's something when we get to chapter 6 that we'll talk about simplifying this a little bit. We'll say, well, if the width is 1 in all of them, could we factor out a 1 and just do it one time, right? But right now I want you to think of this as rectangle. I want you to think of this as rectangle height times rectangle width, which is rectangle area number 1. This is rectangle width 2, rectangle height 2, rectangle width 2, multiply together rectangle area 2, and so forth, and we add up the 5 rectangle areas. So what we're going to be learning today is going to be a lot about notation, writing this out, looking at patterns, and then simplifying, using some notation to simplify that process. Okay? So with these small numbers of them, we want to be able to draw the rectangles, we want to be able to add them up. Okay, but what happens if we want to make the rectangle area, or we want to make the area more accurate, right? We want to get the exact area under the curve. Now we know we can do that with antiderivatives, but not all problems have antiderivatives. So we want the exact area. Well, 5 rectangles isn't going to do it. What would do it? 100 or 1,000 or 1,000,000? But at some point, are you going to sit there and add up 1,000,000 rectangle areas? No, not even 100, right? So how can we? What can we do to add up 100 rectangle areas or 1,000 rectangle areas and do it without having to add up each one? That's what we're going to try to do today. Okay, that's where we're headed. That's what we want to do. Okay, so are there any other problems on that homework out of the book? It looked like those of you that did it got through it pretty well. Was there anything else that was a concern there? Okay, let's look at sample 2, please. sample 2. Now, I don't know if any of you thought to do this. If you had been on track with what we're supposed to be doing, we'd already done the sample 2 ones, okay? Now, there'll still be a chance. Some of you have come in and asked about ones you didn't get, and that's good. You should do that. There's still a chance later on before we hand them in that we'll get a chance to go over some, but if you're really worried about a few of them, you probably should come in and see me. But I'm going to look at 41 on sample 2. Now, that was one of them we skipped last time. And I don't know if you thought to check the ones that we skipped last time to see if those maybe we could do now. Well, it turns out of the 3 we skipped, one of them we can now do. Okay? So I don't know if you tried it, but if you didn't, let's do it together. Okay? And there were some in sample 1. I think it was 29, said something about volume of a solid, revolving. We can't do that one yet. Okay? I think there was another one in there. The one with all the big fractions and things all expanded out. 28, I think number 28. Now that stuff we're going to be doing this week. Matter of fact, you'll start to see as we get into today's stuff how that kind of matches with number 28 a little bit. Okay? All right, so let's look at number 41 here. So it says, here's a function given as a table. Now, okay, that's fine. That's f of x. At this point, I'm going to totally ignore that table now until I'm ready for it. Okay, all I'm looking at is this function right here, this integral from 0 to 6, f of x dx, which means I want the area under that curve from 0 to 6. But all I know about that curve is these points. I could plot them, I suppose, and kind of get a sense what it is. I don't need it. I mean, it's good to know what we're doing. Okay, but I don't need that. Now, they want me to do a Riemann sum. Okay, now what did we say last Thursday, a Riemann sum? Pretty sure we brought up that term at least once, didn't we? You remember that? Maybe the other one. Okay, a Riemann sum. We're going to write it down in notes here in a minute. But a Riemann sum, it's named for a guy, last name is Riemann, a German mathematician. Riemann sum is simply an adding up of rectangle areas. Anytime we add up rectangle areas, that's a Riemann sum. But I've got, don't write it down right now. I've got it. We'll put it in notes right now. Okay? So what this is asking for, when it says a Riemann sum using the value at the midpoint of each of 3 intervals, they're asking for an M3 approximation is what they're asking. They're asking for an M3 approximation. Now, they were nice to even tell us that the width is 2, which should be obvious, right? From 0 to 6, there's our total width. We're going to do 3 subintervals. 6 divided by 3 is 2. So we should be able to calculate that ourselves. So I'm kind of surprised they even told me that. But, okay? All right. Now, if it's helpful, I can come down here and make myself a little graph. I sometimes like to do this. And then I would say, okay, if the width is going to be 2, that gives me 2, 4, and 6. Right? So I think this is helpful to me visually to kind of see what's going on. But I don't care about, where the curve is at this point. All right. So, just like what we just got done writing up on the board, let's write down M3. What's the first midpoint rectangle height? F of 1. Our first midpoint is going to be right there at 1. So we go F of 1 times 2 plus F of 3 times 2 plus F of 5 times 2. My first midpoint's at 1, my next midpoint's at 3, and my next midpoint's at 5. Now, it makes sense that I went over by 2s, because one midpoint was at 1 and then 3. Since each rectangle is too wide, to go from one midpoint to the next, you should have to move over 2. Well, see how easy that is then, when you use F notation? Because now the only thing left is to do what? Grab the numbers. Yeah, there's F of 1, there's F of 3, there's F of 5. So you multiply each one of those by 2. This is a calculator problem even. And you get D, I believe. See? So, now, as you were going through the package yesterday, if you were working through them in a serious fashion, you may have thought some of them were difficult, And that's not surprising because we're just scratching the surface on this. As we go through the rest of this chapter, go into chapter 6, okay, and then the application stuff we do in chapter 7, these will seem much easier, Okay, so it's not surprising, but hopefully as you run through them that you could, you know, say, oh yeah, this is kind of what we're doing now. This isn't too bad. And then maybe look at the solution menu, see what they did, and kind of pick up some things. So that's the goal. So 3 midpoint rectangle areas added together gives us this approximation. Okay, so that's good. So if you understand that and be able to write that notation, that's what we want to have accomplished up to this point. Yes? Yes, right now. As on this first quiz, as we're expanding it out, if I say write out an M3 expansion, remember I said the rule was going to be if it's under 10, we're going to write it out, okay? Which on this quiz, they'll mostly all be under 10. When you write them out, I want you to put the 2 and the 2 and the 2, right? And again, because, and you'll see a little bit today as we do this, when you see this, I want you to see height times width, height times width, height times width, because I want you to see right. That's what we're doing. All right. So, in your notes, a couple of things here. This first one you don't have to put in your notes at all. I just want to walk through this. This is just basically what we've been just writing right now. So I don't take the time and effort to put this into your notes. This isn't a crucial thing right now. But if I had some area over here from A to B, okay, and I want to subdivide it up. This is just some notation stuff. So, like here I wrote x sub 0. We always start with x sub 0 because remember, if we want to divide, remember that one we did on the board, if we want to divide it into 5 subintervals, we need 6 points to do it. Okay, so if we want to divide it into n subintervals, we'll start with x sub 0, then x sub 1, x sub 2, and we'll end with x sub n. Okay, so we'll need one extra one. So that's why we start with x sub 0. Okay? So if we were doing a left approximation, the first height would be at f of x sub 0. And then f of x1, dot, 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 dot. And the last one would be one short, right, of the end, which would be f of x n minus 1. Okay, so that's what that notation means. And of course, the delta x is just our width. The delta x, that just means change in x, which is our width of each subinterval. So delta x is the width. Okay, a right rectangle would start at x sub 1. So this is the same thing we were just talking about when we were looking at that problem number 5. Start at x sub 1, then go x sub 2, and it would end at the far right edge, x sub n. Midpoint, I just called it M1 and M2 for first midpoint, second midpoint, third midpoint, and then, oops, that should be M sub n on the end there, the nth midpoint. Okay? And then trapezoid, same thing. It would start with f, the first 2 together would make a trapezoid, then the next 2, you know, and then on and on. Then the last one would be f of x n minus 1, f of x n. But, so that's what we're talking about. So that's just kind of a generic way of writing what we just talked about in problem number 5. Okay? Now, here's what we can write in our notes as far as Riemann's sum. Okay, except I have one mistake in here I need to fix. All right, so first we'll look at this, this first line here. Okay, a Riemann sum. Think R for Riemann, R for rectangle. A trapezoid sum is not a Riemann sum because trapezoids aren't rectangles. So a Riemann sum is an adding up of rectangle areas. Now those could be left rectangles, right rectangles, midpoint rectangles, or actually some other type of rectangle that doesn't even hit a left or right edge or a midpoint. And I'll show you an example here in a second. All right, so the reason I put C1 and C2 and C3 in there is it doesn't have to be a midpoint. I didn't want to put x sub 0 because those are the endpoints. You know, x sub 0, x sub 1, x sub 2, x sub 3. Those are the endpoints of your subinterval. It could be any point in the subinterval. Okay, so by the technical definition, C1, C2 are just any point in each subinterval. But basically what you have here is a rectangle height times a width. Now notice here I put delta x1 where we hadn't been putting that before. And we'll talk about that in a minute. Delta x1, delta x2, and so forth. Okay? So this is height 1 times width 1, height 2 times width 2, on and on until the last height times the last width. And then we add those up and call it S for sum. That's a Riemann sum. Adding up of rectangle letters. Now, why do you suppose we put a 1 here after the delta x1 and delta x2? Why do we need width 1, width 2, width 3? Why can't we just talk about the width of each one? Because they might be different. Now, 99% of the time in here, we will use equal widths. We'll say, here's your interval, divided into this many equal subintervals. And so our width will always be the same, but it wouldn't have to be. Now, I've got a picture here in the book. I apologize to those of you watching the video, but okay, here is a picture. This picture we're looking at is on page 351 down at the bottom. This is a Riemann sum. Okay? It's 6 rectangle areas added together. They're not equal width rectangles, but that's okay. We just aren't going to deal with those very often, so you mostly don't have to worry about it. About the only time we deal with them is when we have a table of data and the data isn't given to us in equal intervals. So then we just have to deal with it. Okay? But you've got 6 rectangle areas being added up. That's a Riemann sum. Look at this first one. Looks like it hits the curve kind of at the midpoint. Look at the second one. Looks like it hits about at the midpoint. The third one hits where? At the right edge. What about the fourth one? Kind of at the right edge. What about the fifth one? A little past the mid, right? Looks like it hits it a little past the mid. That's okay. And this one, again, hits kind of past the midpoint, maybe 2/3 of the way or whatever. So these last two wouldn't be midpoint rectangles or left or right rectangles. They're just, but they are rectangle heights in this subinterval. They just picked a point over here as what they call their sampling point. It's still a Riemann sum. If it's an adding up of rectangle areas, it's a Riemann sum. Okay? All right. So it's kind of a technicality, but it's important to understand. All right, now, how many rectangles make a good approximation again? Like 1,000 or 1,000,000 or a bunch of them, right? So we might be adding up a lot of rectangles. Well, it might be to our advantage to be able to write that in some shortcut way. And that's what this is. You guys remember this last year? I don't know if you worked on it real long. Some of you are saying, yeah. A lot of people said no in the other class. This E-shaped thing is the Greek letter sigma. This is sigma notation. Kind of the Greek S for sum. That's why we use it. Okay? Sigma notation. Okay, this is an I right here. This weird-looking banana peel thing is my cursive I. Okay? And I, J, and K are usually used for sigmas. Okay? Now, before I come back to this, you can go ahead and write this down, and then we'll come back to it. So, we need to do a little bit of refresher about sigmas. Okay? Because this sigma notation is going to play an important role in what we do today. Now, it's pretty easy. Okay? It's all about patterns. Okay? And finding patterns and seeing patterns and how we write it will be important and so forth. All right. But what this is saying is we're going to add up n terms that have this pattern to them. All right? Now, I'm going to skip ahead a page, and you can jot this down if you want to. I've got a couple sigma problems worked out here. Okay? Here's the first one. And on your homework, you're going to have some of this. Okay? All right. But the way you read this is sigma of 2i squared plus 1, I equals 1 to 5. Now, what this means is I is going to start as a 1, and then be a 2, and then be a 3, and then be a 4, and then be a 5. Any of you that have any programming background know there's a command in basic language that says for I equals 1 to 5, and when you do that, I can go backwards, it can go negative, it can go in increments of 2, it can do all kinds of things. That's not true with sigma notation. Sigma notation, whatever this starts at down here, is its first value, starting value, initial value. I starts as a 1, and then it has to increment by 1s every time until it gets to this value. Okay? So what this is saying is let I be a 1, so you plug it in, get 3. Then you let I be a 2, and you plug it in. 4 times 2 is 8, plus 1 is 9. Then you let I be a 3, you get 19. You let I be a 4, you get 33. You let I be a 5, you get 51. Then you add them up, because that's what sigma means. Sigma means sum. Sigma means take the terms and add them up. It adds up to 115. So there's going to be some problems in your homework, very simple like that. Here's a sigma notation, expand it, which means write it out, and then find the sum. Okay? Now, we can type this into a calculator. In the template where derivative and integral's at, there's a sigma there, and you can type this in. Okay? But if it says expand it out, which on the quiz, I'll probably have you expand it out. I want you to write each of the terms. Okay? But there won't be that many. Okay? Now, here's one down here that starts the initial value with I being 3. You don't have to start the initial value at 1. However, in our sigma notation, we'll almost always start the I at 1. Now, in the book, sometimes they use J and K instead of I. Those are the alphabet ones we use most of the time for sigma, I, J, and K. All right, here I started at 3. That's fine. Start at 3, put in a 3. 3 minus 7 is -4. But then it has to go to a 4. You get -3. Then a 5. Then a 6. Okay? And then you add them up. Okay, that's it. Sigma notation. Not hard at all. Okay? Now, what we're going to spend some time on over the next several days is writing sigma notations. Now, that's where this pattern thing comes in. So as you look at this, you've got n terms being added up. So we write sigma I equals 1 to n. And then where's the I? Where does the I come in? Well, the I is, in the first term, the subscript is a 1, then a 2, and then all the way to an n. The F, the C, the parentheses, the delta X, those all are the same in every single term. So you can see how it just writes like this. Think about it. If I is a 1, this will be F of C sub 1 times delta X sub 1, which is that term. When I is a 2, this will be F of C sub 2 times delta X sub 2, which is that term. Right? So it's just like what we did there. When you expand the sigma out, it would expand out to this. Okay? The last term will be n. So F of C sub n times delta X sub n. You get that. It's a shortcut way of writing a sum. Now, why would that be to our advantage? Well, if I ask you to do this, you don't have to write this down. Okay? No calculator. What would that be? 1 plus 2 plus 3 plus 4 all the way out to, well, that would be a real pain, right? To do that on your calculator. That would be a real pain. 1 plus 2 plus 3 plus all the way to 100. Just like adding up 100 rectangles would be a real pain. Adding up 1,000 rectangles with areas would be a real pain. Now, we can get our calculator out. Go ahead and do that. Get your calculator out and type that in as a sigma real quick. It's just in the same template that your derivative and integral thing is. What do you get? 5,050. Okay. Now, the story goes that a famous mathematician named Gauss, when he was in first grade or very young, was in school, and he was so smart that he was a pain to the teacher because he was, he knew everything, evidently, I don't know, but he would get in trouble a lot. And one day he got in trouble, and so she sent him to the corner of the room and told him to add up the numbers from 1 to 100. Now, he's a young child, thinking this would take him a long time. So he would be back. And he comes back in about 30 seconds and he had the right answer. Right? How did he do? Well, so the story goes. I don't know that this is necessarily true. But so the story goes that he did this. He realized that he could pair them up. I think so. Yeah, he was a genius. Grew up to be. Each pair adds up to what? How many pairs? $101 times 50 is, now if he's a first grader and can multiply, I don't know. So maybe he was a smart kid. 5,050. Now, what this leads us to is actually a pattern, where a formula. There's actually a formula for doing a sigma I problem. The formula is you take the number of pairs, which would be n, this would be n up here, divided by 2, right? That'd be the number of pairs that you have. And then each pair adds up to what? The first term, 1, plus the last term, which would be n. Now this is usually written as n times n plus 1 over 2. Okay? Number of pairs would be this. The number you're doing divided by 2. And then this. So if I ask you to add up the numbers from 1 to 20, you could write that as a sigma. I equals 1 to 20. Sigma I. Well, then that would be like putting a 20 there. So it would be 20 times 21 divided by 2. What would that be? 20 divided by 2 is 10. 10 times 21. 210. So if you added up the numbers from 1 to 20, it should add up to 210. But that's a shortcut for doing sigma I. Okay, now you'll see here a little later where we're going to need or where we'll use that shortcut for sigma I. Let me give you a couple of other of these shortcuts, and they are right here on this page. Okay, now you should go ahead and write these down, but on the quiz, I will give these to you. You do not need to memorize these, but you are going to need these for your homework. Okay, there'll be a few problems on the homework where you will use these. So you might want to have them in your notes. And on the quiz, I will say, you know, use the formulas at the top of the page to evaluate the following sigma problem. And those formulas will be up at the top of the page. Okay? Now, let's just write one at a time here. This first one is for a problem like this. I equals 1 to 5 of sigma 3. Just a constant. C is just a constant. Okay? The I is your variable down here. But C is just a constant. Well, what would this expand out to if you just had a 3 there? When I is a 1, what do you get? When I is a 1, what do you got? 3. When I is a 2, 3. When I is a 3, right? I mean, there's no I even in the problem. It's just a constant. So you're adding up 3 how many times? 5 times. 3 times 5 is 15. So whenever you've got a constant, from 1 to n, you simply take the constant times how many of them you're adding up. Pretty simple. Okay? The second one here is the one we just did. The Gauss one. Okay? And then this one is if you had a sigma I squared. Yes?
What if I doesn't start?
Great question. Then you can't use these formulas. So it will start at 1. Or we'd have to rewrite it so it did start at 1, which I don't want to get into right now, but we'll see that through the next couple of days. But yes, we want I to start at 1, and we will always start I at 1 if we can. Okay, if we have a choice, we'll want to start I as 1. All right. Now, let's look at a quick sample problem of what that might look like, where we would use those formulas. So I might give you a problem like this of I squared minus 2I. And I want you to, and the directions here are use the formulas to evaluate this. Because think about it, doing it on your calculator would be a pain. Put in a 1, get a number. Put in a 2, get a number. Put in a 3, get a number. You have to do 20 times. I mean, that's getting borderline. I told you with rectangles, if we got to double digits, you could use your calculator. You don't have to write them all out. Okay, well, this is 20 of them. So it would be kind of a pain to do 20 of them. And if that was 200, it'd really be a pain. So what we're going to do is we're going to rewrite this using a couple of rules of sigmas. One of the rules of sigmas is you can split it apart when you have a subtraction. So we can split this into sigma I squared minus sigma 2i. Does that look familiar? Just like an integral, right? Just like a derivative. We can split it apart. What do you suppose we can do with that 2 on that second sigma? Bring it out front. Now we can use our formulas. Right? Now we can use our formula. So, what's sigma I squared? I equals 1 to 20. 20 plus 1, which is 21. Because 20 is the end. This is the end right up here, right? And then 41 divided by 6. And then this would be a 2. And then what's sigma I? 20 times 21 divided by 2. Get out your calculators. All right, this is like 420. I don't know about this one. Help me out. 20 times 21 times 41 divided by 6. 70. And then subtract 420. 2,450. Now, use your calculator sigma to double check that. Just type the original problem in. I'm trying to think if this will be a calculator problem test or not. I mean, if I say use the formulas, then I'll want to see this work. I want to see you split it apart, pull out the 2, use the formulas. So, so I may still let you use your calculators so you can do the arithmetic here. But now when you type your sigma in, is it the same thing? Okay, that's kind of cool. So the calculators will do that sigma for you. But these formulas are important to use too. Okay. Now, they were a lot more important before we had these really cool calculators that we could just type sigmas in. I mean, you know, 20 years ago, 30 years ago, you could do it on a computer, but you didn't have near the access to that. So you obviously, did this by hand a lot more. But anyway, so we're going to be using that. So all these little things we're talking about today is all going to come together, hopefully, in a really cool way as we get to this. But this is just using sigmas to, write sums. And these are some shortcuts when you get sums that are so big that you really don't want to sit there and add them up by hand. So that's where these formula shortcuts come in. Now, the formula shortcuts are kind of limited. You have to have things that are written as I and I squared and constants, and that doesn't always work that way. If we had a sine or e to the x, then these are no good. So then it gets more complicated. So we'll stick with some simple ones for right now. Okay, so let's go next to the actual goal of class today of what we want to get done. So let's see. It says right here, stand up, take a break. 45 seconds. Okay, stretch, because we got to get ready for the big grand finale here today.
By the way, I liked all the things that you wore that shirt.
Stand back there.
Oh.
All right, that's it. Have a seat, have a seat, have a seat. Now, so what we want to do is we want to put together this notion of how we write out these rectangle areas, and we want to combine it with this, what we talked about sigmas, and bring this all together in kind of a cool way. So here's the problem we're going to deal with right here. So everybody write this down. Integral from 0 to pi of x squared dx. All right? Integral from 0 to pi of x squared dx. Now you might want in your notes, you might want to start this at the top of the page. I don't know. This may take some room. This is kind of a big deal. This might be a page you want to save. Laminate. You know, put up on your bulletin board. I don't know if we get on that. Problem of the day. Problem of the year. I don't know about that. I know some people there. Well, I don't know. You'll see. All right. So first of all, let's just start out, because this is a simple one where we could draw the picture very easily, and we could actually get the exact area pretty easily. So let's go ahead and do that, even though it's not necessary for the rest of what we're doing. But this would be just a basic parabola. All right. We'd be doing the area from 0 to pi. So we're talking about this area right here, right? The only way we could actually calculate that area would be what? Fundamental theorem part 2, right? So tell me what to write. 1/3 x cubed, right bracket, 0 to pi, plug in the pi, 1/3 pi cubed minus 0, so 1/3 pi cubed. Which, let's get your calculator out and just, that doesn't mean much to me as an area, just give me an approximate decimal for that. 1/3 pi cubed. Should be positive area, obviously. 10.335. Okay, makes sense. Okay, area of about 10.335 is roughly what we have there. So that'll give us a nice comparison, because remember, we've said when we do an integral, and if somebody in the air class said antiderivative and integral are not the same thing. An integral is the area under the curve from 0 to pi. There are 3 ways we can find it. One is geometry. That doesn't work on this one. Fundamental theorem part 2 with antiderivative, which works here, but it doesn't work if you can't do the antiderivative. And so the only other way you could then do one would be approximation. So we're talking about approximations right now. But what we want to do is do one where we know the exact answer so we can compare and see what we're doing. And then, of course, what our goal here today is to actually use this to add up to get the exact area by adding. And that's what we're about today. So let's go to it. So we're going to start by doing an R4 approximation. Now, 4 right rectangles is hardly ever going to be a good approximation. I mean, when you do 4 right rectangles, just not going to be very good. Okay? All right. Now, what I might do to start this problem is draw myself a little picture. Go 0 to pi. I don't even care about the parabola. I know we did it before, but normally I wouldn't even care about what the function is, right? Like we were talking about. And I'm going to divide this into 4 subintervals. Right? So I'm going to have 1, 2, 3, 4 subintervals. What do I need to calculate next? The width of each interval, right? So what's the width going to be? B minus A divided by N, right? I minus 0 divided by 4, pi over 4. So my width, that's my delta x, right? That's the delta x that we've been talking about. That's the width. All right. So what is my first rectangle height? And these are right ones we're doing now. F of pi force, because this first one here is going to be pi force, right? So F of pi force times pi force, right? Now what's my function? F, it's x squared, right? But I don't even care about that, right? I want to do F notation, all right? What's my next right input? Hold it. Stop right there. Okay, look up here. This first one is pi force. Then I move over pi fourths. What's my next one? 2 pi fourths. Now, why in the world would I want to leave that 2 pi fourths? The next one's going to be 3 pi fourths, and I'm actually going to write my last one as 4 pi fourths. Now, why? Well, because we're going to be doing sigma notation, and sigma notation is much easier to write when you can see the pattern. And seeing the pattern is usually easier if you do not reduce things. So, kind of what opposite of what you're used to. We do not want to simplify that. So I'm going to write that f of 2 pi fourths times pi fourths plus f of 3 pi fourths times pi fourths plus f of 4 pi fourths times pi fourths. All right, now it's only 4, so we're going to get our calculators out. We'll cheat a little bit. I want you to go into your calculator, okay? Go on the calculator screen and define, remember we talked about this last Thursday, define f of x to equal x squared. That'll shortcut a few things for us here. Define f of x to equal x squared. So this is a trick. You can do this on the quiz. Okay, if we have a problem like this and I ask you to expand out an R4 approximation, you could write it out in the F notation. That'll be fine. Then you can go to your calculator to add it up. Now, one of the things that you will possibly do, now that what we're going to do here in a minute, is we're going to write the sigma notation for that. And you might decide it's faster to write the sigma notation and use your little sigma notation in your calculator to add it up for you. Okay? It doesn't matter. Okay, but right now we're not writing the sigma yet, so let's just, so define f of x to equal x squared, right? Which you can just type out the word define if you want. It's also in the menu. Now just type this out. Just type f of pi fourths times pi fourths. And if you want to, you know what, if Steve, if right here you want to factor out the pi fourths right here and save it to the end and just do it once, that's fine, right? So, right, if you factor out a pi fourths, so you could type in right now f of pi fourths plus f of 2 pi fourths plus f of 3 pi fourths plus f of 4 pi fourths. Hit enter to get that answer first, and then times all of it by pi fourths, that's fine. And it might be good to hit control enter so we get a decimal here and not some weird fraction. Actually, somebody do it where you don't hit control enter and tell me what you get, the weird fraction. But then also get the decimal. You get 15 pi squared over.
Oh, wait. Oh, no.
Oh,
Raise it. I didn't times it by the pi fourths.
oh, okay. Well, it's going to be pi cubed then. Over 32. Right? And then what is that as a decimal?
11.
Ooh. 14 sounds better. 5, 3, 4, 5. Now that's too big, right? Compared to our actual answer. Does that seem reasonable that it's too big? If you go back to our picture, our original picture, if you put right rectangles in that, aren't they all going to be over? Yeah, they're all going to be over. So it makes sense that that's too big of an approximation. Okay? Now, let's talk about this. Let's talk about this sigma thing I was just mentioning. Okay? Let's talk about the sigma business. One of the things you're going to do in your homework today, what's the matter? We're not getting. You had it right.
But I didn't, when I hit control enter, it's 15, 14, 25.
It's taking some function from
Oh, well, okay, you did previous answer. I took it times pi fourths again. Go up and grab. Go up and grab that. Hit enter. Now hit control. See, well, no, you didn't. You just hit control enter and took the previous answer times pi fourths.
You didn't factor it out? Okay. This didn't work either. I just typed the whole thing out.
Did you define f of x equal x squared?
Yeah.
No, you defined it. define it to equal x squared. Define f of x equal x squared. All right, now, all right, look up here now. This is the important part. Type in your calculator is not the important part, okay? The key part here is now, could we write this expansion as a sigma? Okay? Because that's one of the things you're going to have to do in your homework. They're going to give you a pattern of things all written out, and you're going to try to write the sigma. Well, we'll start with I going from 1 to what? No. No. 1 to 4. Because remember, the sigma is at how many things are you adding up? That's what that top number is. How many things are you adding up? How many are we adding up here? 4. We're adding up 4 things. This, plus this, plus this, plus this. So the 0 and pi in the integral are different than the 1 and the 4 here. Okay? That's the things you're adding up. Okay. Now, what's going to go inside of here? How do we generate each of these terms, and where's the I at? The I is a 1, then it's a 2, then it's a 3, then it's a 4. What do you see in there that's a 1, then a 2, then a 3, then a 4? The number of pi's on top. What about the F? Does that change in all of them? The parentheses change in any of them? What about the 4 on the bottom? What about the pi force width? So those are all going to be in the formula and will be unaffected by any i's that you have. So these things are in every single term. When i's a 1, those things are going to be in there. When i's a 2, those things are going to be in there. When i's a 3, those things are going to be in there. But the only thing that changes, the top, 1 pi, 2 pi, 3 pi, 4 pi. So in my sigma, I what? I pi. Exactly. I pi a, oh, okay. I pi over 4, right? Now, you're right, it would be I pi over 4 all squared if we want to plug it into the function. But let's stay in F notation. But we are going to go there here in a second. Okay? But since we have defined our function to already be x squared, we don't need to plug that in. We can just do it on our calculator. So we're going to do 2 things right now. First one's the easy way. We're going to do it on our calculator. So you've already defined f of x to be x squared. So go ahead and just type this now into your calculator with sigma notation. So go to your template there, grab the sigma, type this in. Again, this is typing it in on sigma on your calculator is not something you're going to do on the quiz, maybe to check an answer or something. Now you might think, it's too bad, it's easy. But, okay, I'm not really quizzing you on whether you can get your calculator out and type in the sigma. Hopefully, if you type that in correctly, it should give you this answer right here. 14.534 or whatever. Okay, now, this is kind of cool. Not the coolest thing today, but it's kind of cool. Is we could go ahead and now kind of do this part by hand a little bit. In other words, we could take the next step, which on this sigma, we could actually take, I mean, right here where it says f of I pi over 4, we could take I pi over 4 and actually plug it into the function, right? Take I pi over 4, plug it into the function, which means you get I pi over 4 squared. Now, you don't have to write this part down if you don't want to, okay? Not crucial right here, okay? But we can take I pi over 4 and plug it into the function x squared. So we get that. Now we can do a little algebra to this, okay? And let's see, if we square that, that'd be I squared pi squared times pi. So what would that be? I squared pi cubed. And the bottom would be 4 squared is 16 times 4 is 64. Correct? And this would be I equals 1 to 4. Right? Now, I could pull the constant out in front. Remember we did that with that 2 that one time? Now, what's constant inside here right now? 64 and the pi cubed, right? But I is variable. It's a 1 and a 2 and a 3 and a 4. So I can pull the pi cubed, start to see it a little bit probably. And in here I'd have sigma I squared. Now where have we seen a sigma I squared before? Those little formulas we wrote down a minute ago, right? So look at that formula. Look at that formula we had a minute ago. And what's our n for our formulas here. Our n is 4, right? So this would be pi cubed over 64. And then the formula was what? So that'd be 4 times 5 times 9, because it was 2n plus 1, all over 6, right? So we could cheat, we could plug in our calculator, or we could just say, hey, 3 goes in there twice, 3 goes in there 3 times. Let's see, 4 goes into there 16 times. What do we got? 3 times 5, look at that. 3 times 5 is 15, pi cubed over 32. So we can kind of do it a little old school, set up our sigma, do it this way, use our formula, right? But all of this, don't forget, all of this was simply adding up 4 rectangle areas. All the fancy sigma stuff and the formulas, all it was adding up 4 rectangle heights times rectangle widths. That's all it was. But what was the advantage? What could possibly be the advantage to writing it in this notation and maybe going through this? Because that seems just as hard as doing 4 rectangle areas. So writing all that didn't seem to be that big of an advantage. Okay, thanks, John. Let's do R100. We were going to anyway, but I'm glad you said 100. If you want to do R100, let's start writing it out at least, but we're not going to type in 100 right rectangles. So what would change here? Well, still going 0 to pi. What's my width? Pi minus 0 divided by 100. Right? So my first would be at where? The integral starts at 0, so the first width over would be pi over 100. What's the second one? 2 pi over 100. See why you wouldn't want to simplify it? What's the next one? 3 pi over 100, 4 pi over 100, 5 pi over 100. What's the second to last one? 99 pi over 100. And the last one? 100 pi over 100. Right? Okay, so we can do this. So our first rectangle height would be f of pi over 100 times my width, pi over 100. Write that down. Plus, next one, f of 2 pi over 100 times. Okay, I'm tired of writing already. So we're going to dot, dot, dot it. And what's the last one going to be? 100 pi over 100 times pi over 100. Now, I don't even want to type that into my calculator. The calculator's nice, but I'd have to type 100 of those. So I don't want to type that whole thing out. So what would be much shorter? Make it into a sigma. Now, how hard is that going to be? The sigma is going to go from 1 to 100 this time. And we look for the pattern. Well, when I is a 1, f is going to be f. The 100 is going to be 100. The pi over 100 is going to be 100. The only thing changing every time is 1 pi, 2 pi, 3 pi. So this is what? F I pi over 100. Well, look how easy that is compared to the one you just had. Matter of fact, if you just type this in, just arrow up on your calculator, grab this one, change the 4s to 100s, and you got it. Which means how quick and easy would it be to do 1,000 rectangles? Or 1,000,000 rectangles, right? I mean, once you have this written out, now we can do as many rectangles as we want. So this notation is very powerful. Very powerful, let us do this. Okay, so tell me what you get, and let's do it without hitting Control Enter. Just hit Enter, and then hit Control Enter. Ooh.
6,000.
Okay, I'm not going to write that. Hit Control Enter.
10.49.
How much?
10.49.
Okay, now that's approximate, not equal. That's almost the right answer. It's a little bit over. It's always going to be a little over if we do right rectangles on this particular function, right? Right rectangles are always going to be a little bit over, but by gosh, it's a lot better approximation, right? And 1,000 would be better yet, and 1,000,000 would be better yet, right? It's always going to be over. Now, pretty soon it's going to be over in like the 9th decimal place, but then we wouldn't even care, right? So we're getting a better and better approximation. What if I said then, well, let's use rectangles to get the exact area? How many rectangles do we need to get the exact area? We need an infinite number of rectangles, and here's where it starts to get really cool. So we need, I know I shouldn't have to tell you that, but sometimes I got to tell you when we're going to do it. Okay, right here, we're going to do R sub n. We're going to do n rectangles, and then we're going to let that go to infinity. Okay, so now, what is, how many are you doing?
A billion.
It might take a little while. Yeah. Yeah, it takes a little while to think about it. Now, when you realize how many calculations it's doing, yeah, you kind of get the picture why it would take a little bit of time. All right, so 0 to pi, and we're going to do n subdivision. Now, you're going to have some of on your homework that have n's in them, so this sometimes gets a little trickier. What's going to be the width of n rectangle? Pi over n. I mean, it's still b minus a divided by the number of subdivisions. So if you go pi minus 0 divided by n, that's pi over n. So what's the first right edge? Pi over n. What's the next right edge? 2 pi over n. And the last one is n pi over n. N pi over n would be the last one, right? So I'm not even going to write out the whole expansion. I think we can go, since we got these other ones up here, right? We can tell what it's going to be. It's going to be f of pi over n times pi over n, f of 2 pi over n times pi over n, right? I mean, you can see what it's going to be. So I think we can go right to the sigma. It's going to go from 1 to n. It's going to be what? F of I pi over n times pi over n. Now, this is a little harder to think about putting in your calculator because we're not going to get an actual number, you don't think, because these n's are in here. How can we get an actual number if we don't have a number of rectangles? If we have an infinite number of rectangles, how in the world can we actually get a number? Well, here's where these formulas are going to come in, and we're going to do it like we did up here. So I'm going to actually take this out of F notation here. Okay? I'm going to take this out of F notation and I'm going to plug it in. So I'm going to take I pi over n and put it into the function x squared. So that would be what? Take I pi over n, plug x. So it'll be I pi over n all squared times I pi over n, or excuse me, pi over n, pi over n. And then I is still going from 1 to n. Now I'm going to do just like I did up here. I'm going to square this. So this is going to be I squared pi squared times pi. So that's going to be I squared pi cubed over n squared times n. It's going to be n cubed. Oops, we got the sigma. Okay? Now I'm going to pull the sigma out, or the constants out in front. Now what are the constants in this problem? The pi cubed and the n cubed. Because n's a constant too. It's the number of subdivisions. That's not going to change. Once we pick a number of subdivisions, that's it. So we're going to take the pi cubed over n cubed out in front, and we're going to have our sigma 1 to n of I squared. Oh, okay. So we're kind of where we were with this one. So I'm going to have pi cubed over n cubed. What's this now? Sigma I squared. I equals 1 to n. So it's n plus 1, 2n plus 1 over 6. Okay, now we're going to stop for a second because we don't have anything to plug in for n, so we can FOIL this out and get a whole bunch of things with n's, but then we got to stop and say, wait, how many n's did we want? How many rectangles are we trying to add up here? Infinite. We can't put an infinite symbol here, by the way. Okay? But what we can do is out in front do the limit Now you mean that in a good way, right?
Yeah.
Oh my gosh. Or maybe not. Okay. So limit as n goes to infinity means over here we're doing the limit of this as n goes to infinity. How did we do limit problems as n goes to infinity? One way to do it was high powers dominate. This one is tailor-made for high powers dominate. Because if I was to FOIL this out, it's easy if all I care about are the high powers. What's the highest power if I FOIL that all out? What about the 2? It'd be 2n cubed, right? The highest power term, if I FOIL this all out, will be 2n cubed, because it would be n times 2n. So this would be 2n cubed. 2n cubed, don't forget about the pi cubed. Almost there. Over 6n cubed. The n cubes cancel. So it'd be what? 1/3 pi cubed. Isn't that awesome? Wait, some of you haven't seen it yet. Some of you haven't seen it yet. Why is that awesome?
That's the exact answer.
Because that is the exact answer of the area. See? The infinite number of rectangles gives the exact area. Now, this is really cool. It's limited in its usefulness only because we got an I squared, only because I picked this function to be x squared. I mean, we could do it with other functions like sine x or e to the x. It's just that the limit we get to right here would be a lot more complicated to do. We couldn't just do a high powers dominant. But today wasn't about as much usefulness as it was about theory and the concept. And this is the equivalent now of doing the long way. Remember we did the long way with the derivative thing, f of x plus h minus f of x all over h? The good thing about this is you're not going to have to do this on a quiz like you did with that. Okay? You're not going to have, yeah, you'll do parts of this, like where you use the formula a little bit, that kind of stuff. Okay? All right. Now, I want you to look on your book, in your book on page 353. And so, okay, where this all comes together then, and again, this is more about theory than usefulness. Fundamental theorem part 2 is much more useful. I mean, we did that in just a couple of seconds at the beginning of the problem. But again, that only works if you have an actual, something you can do an antiderivative on, all right? So rectangle approximation are kind of important, but this is, now this, you don't have to write out this whole thing, but you could write down just the result of it right here, okay? So the actual integral, the actual area under a curve, f of x. So it says, let a function f be defined. You don't have to write all this word stuff, just the stuff above. The integral of f over ab, denoted the integral from a to b f of x dx, is the number, if one exists, to which all Riemann sums tend. That means rectangle areas. All rectangles areas tend as n tends to infinity. Then they add a little technicality here as the widths of all the subdivisions go to 0. Well, think about it. If you have 100 rectangles, 1,000 rectangles, 1,000,000 rectangles, what's happening to the width? Smaller and smaller and smaller. That is assuming they're all equal. I mean, technically, remember that picture where we had the 6 of them and they were all unequal widths? Technically, you could have that situation where you had one big fat rectangle in the middle that never shrunk, and all the other ones did shrink, and you could go to infinite number of rectangles, but you'd never get the exact area because you got that one rectangle that doesn't shrink, you know what I mean? It's a technicality that is not a big deal. So they do have to throw in there that we have an infinite number of rectangles and all of the widths are going to nothing. Because that's what happens. When you get an infinite number of rectangles, that means the width is nothing. Well, then how do you have area? Well, the width doesn't actually equal nothing. It's going towards nothing. Okay, again, that's that idea of limit. The limit, we don't really have an infinite number of rectangles. The number of rectangles is going towards infinity, which means the widths are going towards 0. Now, along those lines, look at these two. look at this sigma notation, especially inside the sigma notation. Doesn't that look an awful lot like our integral notation? Can you see where the dx comes from? Where's the dx come from? The width, right? And what did we say? As we get to an infinite number of rectangles, what's the width? It kind of disappears. Kind of disappears. That's why when we talk about this dx, we say it doesn't really mean anything. It's just kind of there. Well, that's why. It comes from this idea of the delta x, the width, which is actually kind of disappearing. So when we actually talk about the exact area, there really isn't a width to talk about. So it becomes this dx thing that we just say, well, means with respect to x. But now you can kind of see where the notation comes from a little bit. It's kind of like saying, hey, height of the function, width of the function, multiply those together. So from this point on, you will hear me often talk about an integral not only as areas under a curve, but I will talk about the integral as an adding machine. Because that's really what an integral is an adding machine. It's adding up a bunch of pieces of f of x times delta x, height times width. It's adding up a bunch of areas. One of the questions on your next quiz will probably surround this, and it will probably be something along the lines of, explain how this is the exact area. Well, let's go through it. How is this the exact area under the curve? Well, what is f of c? As opposed to rectangles. There you go. You're making it too hard. It's a rectangle height. F of c sub I is a rectangle height. What's delta x? Rectangle width. When you multiply height times width, what do you get? Area. So this times this is the area of a bunch of rectangles. What's the sigma do? Adds it all up. So the sigma adds up all the rectangle areas. And then what's this do? Makes you have how many? An infinite number of rectangles. So looking at each piece, you can see how this gives you the exact area. Okay? It's taking rectangle areas, height times width, to give you each rectangle area. The sigma adds up all the rectangle areas, and the limit means you're going to add up an infinite number of rectangle areas. And when you add up an infinite number of rectangle areas, you get the exact area. Okay? All right. So you can see where finding a pattern is important in writing the sigma. Writing the sigma is important because if you want to add, like John said, if you want to add up 100 rectangles, you don't want to type in 100 rectangles added up. You can put it into sigma notation. You put it in sigma notation. We use these formulas to sometimes simplify. Okay, and we can do some of that. But the key to all that is just to understanding the concept of integral, meaning area, means adding up a whole bunch of rectangle areas, actually an infinite number. And that's what the integral is. And we will refer back to this when we talk about story problems and units and why doing an area is finding the distance traveled under a velocity curve. We'll talk about how that is, okay, and what that's all about. Okay, so your homework for tomorrow is going to be on the page on the assignment sheet here. And I've changed it a little bit. Okay. For those of you watching the video, you can't see this. So on the LH page 279. Now that's a different LH packet, an earlier LH packet than the one we've been working lately. The LH packet, you can tell because it got sigmas on the front page. Okay. The front of it is page 279. You can see there's a bunch of sigmas there. Okay. So that's the LH we're looking at. Okay, now I've kind of taken a few off from the LH packet, and then I've thrown in a few from the book here that we're going to do for tomorrow. And the ones in the book are sigma. So now most of these are just working with sigmas, giving you a chance now that you sat here and watched me do all this. It's going to give you a chance to work with some sigmas, write some sigmas, finding patterns, stuff like that. So giving you a chance to now do some of the stuff that we were doing today, the pieces. So do these problems here. Now I changed the 19 through 33 odd to 19 through 27 odd. And then on the next line, 5.7, pages 362, just do 1 through 4 and 5 through 11 odd. A lot of those don't take very long. A lot of those are just expand out a sigma, just simple little sigma ones. Write a sigma. Hopefully if you see the pattern, that's not too hard to write. Kind of this I pi thing. You know, we did I pi over 100 on that. Okay, then we've got a day or two here of just working some more with this idea of sigma and the integrals and getting it all clarified, and then quiz on Friday. Okay. We wrap up this idea before spring